Here is a somewhat quick introduction to surface integrals, which is the fifth of 5 types of integration that you will now know how to do. So I'm showing you slides and a doodle pad. On the doodle pad here, I sort of have an inventory of the different kinds of integration that you already know how to do. There is the Calculus 1 style integration, where you had a one-dimensional integral of a function of one variable. So you had an interval of integration, like from x equals 1 to x equals 5, integrate f of x dx. Single integrals. And then at the start of this semester, we went for the gusto and we said, well, what if we have two variables and in our function, and we integrate that over a two-dimensional region of integration. Now this becomes a three-dimensional problem because this function would be seen as a surface z equals f of xy. So here we have a two-dimensional integration of a function of two variables. The region D is down in the xy plane. It's like a circle or some two-dimensional region of integration. This surface hovers over that region, and we integrate that function over that region. And then we thought, well, if 2 is fun, imagine how much more fun 3 is going to be. So then we have a three-dimensional region of integration, such as integrating a function of 3 variables inside a sphere, or inside a cone, or whatever, or inside a box, or a tetrahedron, or whatever it was. But nonetheless, a three-dimensional region of integration in which we are integrating a function of 3 variables. So there was a nice match all along between the number of variables in the function and the dimension of the region of integration. Interval, two-dimensional region, three-dimensional region. And then we really mixed things up because we went for line integrals. And here we could do line integrals in 2 space or 3 space, but we go along a contour or a line and we integrate a function of 2 variables or of 3 variables along that line. But whether we're integrating f of xy or f of xyz, our function has either 2 or 3 variables in it. But the domain of integration, the points along our contour, that is a one-dimensional construction. If you clip the 2 endpoints with scissors and straighten it out, you have a straight line based on your contour. And so notice the pattern that's been building here is the number of integral signs that we put on our integral is not counting the number of variables that are in the function. It seems that way, but that's not what's happening. The number of integral signs that you see is counting the dimensionality of the footprint of the integral. Interval, 1 integral sign. Region in the xy plane, two-dimensional, 2 integral signs. Three-dimensional region of integration, 3 integral signs. For a contour integral, it's a one-dimensional region of integration, the contour itself, so 1 integral sign. There's something missing. We haven't done the 5th type yet. And if you understand how this integral is sort of a hybrid of these 2 scenarios, the thing that's missing is sort of a hybrid of these 2 scenarios in which we will integrate a function of 3 variables over a two-dimensional region of integration, which would be a surface. And so comes our surface integral, which might be posed as such, capital S for surface. We're going to walk all over points on a prescribed surface and accumulate values of this function as we move along that surface. Here's some pictures to help with that. Right? Contour integral here on the top. One-dimensional thing of integration. One-dimensional contour of integration. Yes, it's in 3 space, but as a contour, it's one-dimensional. It only takes one parameter to tell us what all the points on this contour are. Line integral or contour integral, whatever you want to call it. Here's what we're moving to now, is a surface integral. The surface is the footprint of the integral. We're going to go on points of that surface and accumulate, in a weighted partition sense, values of this function of three variables. Okay, so in this case, you're the calculus ant, and the calculus ant is walking along this contour, and it has its little function sensor, and it's sensing the values of the function that it's walking through as it traces its path along this contour. Down here, the calculus ant is walking all over this surface, and as it's walking over the surface, its little function sensor is gathering values of this function of three variables that it's encountering as it walks over the surface. That is a surface integral. The calculational engine to this surface integral is to partition the surface itself by basically casting the surface down into, say, the xy plane and making a partition in the x direction and the y direction. Each of those partitions corresponds to a little patch up here on the surface. We take a representative point from that patch, we plug it into the function, we weight that result by the size of this patch, which is also tied to the size of its shadow patch down in the xy plane, and that measures delta S. Now, we're not going to get into a whole long to-do about this because we aren't going to calculate surface integrals using the Riemann sum dynamics. However, you need to know what's going on. And this is the Riemann sum type of definition of a surface integral, by which we have a function of three variables that we are trying to accumulate values from. We walk over the surface and we partition the surface in two directions that shadow the x and y axes, or perhaps the y and z axes, or the x and z axes. It depends on the case, but it's a two-dimensional partition. Within each cell of the partition, we pick a representative point, we feed it to the function, and we take f times delta S, capital S for surface area. This partition happens in two directions. We accumulate all these results, and then we take the number of cuts in the partition to infinity, and this is what we call the surface integral. Now, if Riemann sum definitions of integrals have never made any sense to you before, this isn't going to make any sense either, but I wanted to show it to you at least superficially so that we could say that we saw it and we know what's going on. Now, there's a difference between the presentation of the integral and the form we put it in to calculate it. And here's a flashback to one of these. When we just finished doing line integrals, we were presented something that looks pretty benign, like this. We had an integral over a contour of some function of x and y, ds, where s is the arc length parameter that moves us along this contour. This was the presentation of the integral in the sense that, hey, here's what we would like to calculate. However, in order to calculate it, we had to load it up with all the parametric equation information about the contour. So this contour had a parametric equation for x that got plugged into the function. It had a parametric equation for y that got plugged into the function. And this ds expanded out into x prime squared plus y prime squared dt. So the integral that was presented so nicely in a nice tidy little ds form, that form is not the one we actually calculate with. We actually expand everything out. This is terrible handwriting on my doodle pad, I apologize for that. But we take the integral that is presented for our consideration and we say, well, you know, if you want the number that that corresponds to, we have to unpackage everything in terms of its parametrics, present this hideous Calc 1 type integral in terms of the parameter t, and then do that integration. A very similar thing is going to happen with surface integrals. And here's how. This version of the surface integral, double integral over a surface of xyz ds, that is just the notation that's presented to you that says, hey, you need to calculate this integral of this function excuse me, over that surface. In order to calculate it, we have to expand it according to the equation that describes the surface by leaving x and y alone, replacing the variable z with the equation of the surface, which we'll call g of xy, and then what used to be ds, d capital S, will expand into this horrible square root thing based on the function of the surface, much like in the contour integral case, the d little s expanded into this horrible square root thing having to do with the parameter of the contour. So we can be presented with a surface integral, kaboom, we have to widen it out into this terrible thing, but this is what we evaluate. Where a contour integral was presented in a tidy contour integral notation but then converted into a calculus 1 style single integral for evaluation, a surface integral is presented as a nice tidy surface integral, such as the integral of f of xyz ds. However, we lay it out as a messier, good old-fashioned double integral for evaluation. And here is a summary of that process. The ingredients that we will be given are some sort of statement of the function f of xyz to be integrated, and also a description of the surface over which we are doing the integration. There are two functions in play. There is the function that is being integrated, f of xyz, and then there is the function g, which describes the surface on which the integration takes place. It is that function g, the surface function, that we use in this expanded square root term that will open up the surface integral into a good old-fashioned double integral. You probably never thought you would be saying, oh, thank goodness this is just a regular old double integral, and yet here we are. So let's see a couple of examples. Let's do example 1, where we are asked for a surface integral of the function y ds over the surface z equals x plus y squared, where x goes from 0 to 1, y goes from 0 to 2. Here I have just the general template for one of these surface integrals, and I've written the starting information for this particular case. Naming convention, remember the function being integrated is f, the function describing the surface is g. So to evaluate this surface integral of y ds, we're going to unwrap it by which we find any z's in the function, what used to be xyz, and we say, well, we're not interested in z's anywhere in the universe, we're only interested in z's that are on the surface of integration, and so we would replace z with the equation of the surface. And then we tack on this scaling factor that projects the surface down into the partitioned region of the xy plane, which involves the derivatives of g. For this particular case, in the example, f is just y, there are no z's in it, and then from the equation of the surface, well, that's not so bad. The derivative with respect to x is 1, the derivative with respect to y is 2y. And so, fundamentally, we then turn this into a double integral, right? We're up here now, turning this into a double integral of our function, which is just y, times, and then we load up this yucky square root thing, with gx, the x derivative squared, plus the y derivative squared, plus 1. That's part of the projection. There's a lot of geometry in there in terms of why the heck that plus 1 is present. You can go read any standard textbook should explain that. And here we have a garden variety double integral, where we're doing a double integral of this expanded function over this rectangle. Now that's going to have constant limits of integration. So if we proceed, let's take that dA and unwrap it as dy dx like we normally might, which means our limits of integration for y on the inside will go from 0 to 2, and x will go from 0 to 1. And then the function being integrated is y times the square root of simplified 4y squared plus 2. Right there, just tidied that up. Okay, so now we're in the opening salvo of multivariable calculus back to a good old-fashioned double integral, where at this point you say, that's much better than it looked at the start, and then we go evaluate this. The purists would probably want us to evaluate this by hand, which would require a u substitution. We don't have that kind of time right now. So here is that integral in Wolfram alpha. Let it spin its wheels. The net result, 13 square root of 2 over 3. And that is the value of the surface integral. Let's crank through one more example. Example number 2 asks us to do the surface integral of x squared z squared ds, where s is part of the cone. Z squared equals x squared plus y squared that lies between z equals 1 and z equals 3. So we're doing a surface integral of the function x squared z squared over the surface that's here in the image. Piece of a cone, almost looking like a coffee filter. The plane z equals 1 is the base, z equals 3 is the roof of this surface. And so we're walking over this surface, accumulating values of the function x squared z squared in a weighted partitioned sense, accumulating values of that function over all the points on this surface. Now, remember again, there are two names going on here. There's f, which is the name of the function being integrated. There is g, which is the equation of the surface on which we're doing the integral. You may remember that in order to evaluate this integral, we are going to have to open up the integral with respect to ds into this gruesome double integral where ds is projected onto the xy plane using this nasty square root projection term. So we need to do gx squared plus gy squared plus 1, and in this case it's much simpler to do this separately and then build it in. So remember the g function, well, in this case it's written nicely as z squared equals x squared plus y squared. So my little bracket indicating the right hand side was gx was a little loose-handed there, because g is actually the square root of x squared plus y squared. X squared plus y squared is z squared. So g itself is z, the square root of x squared plus y squared. Now that means that gx is x over the square root of x squared plus y squared, and gy is y over the square root of x squared plus y squared. Those are the two derivatives. So gx squared plus gy squared plus 1 is going to be this squared plus this squared together, x squared plus y squared over x squared plus y squared. That's nice. Plus 1. And hey, that's just 2. Well, what do you know? That's very nice. And so, when we go to load up x squared z squared ds over the surface S, where the surface is the cone z squared equals x squared plus y squared. Over here from the slide, this big term happens to simplify to the square root of 2. So this will become a double integral in the good old-fashioned sense of x squared. Well, now we don't want z's anymore, but remember this is the function everywhere in the universe, where z could be anything. We are only interested in the values of this function on the surface on which z squared is x squared plus y squared. And then this ds is the thing that opens up into nasty square root, which here just turned out to be square root of 2 dA. And better yet, the dA is just the projection down in the xy plane. This is a terrible drawing of that cone. And so the area of integration here is 2 concentric circles. So again, now we're back to good old-fashioned double integral problem. Here's our domain of integration, which is called D for a two-dimensional region, also because it looks like a donut. And we're evaluating the integral of x squared times x squared plus y squared square root of 2 dA. The radius of this inner circle is 1. The radius of this outer circle, well, remember that would be z squared equals x squared plus y squared, where z was 3, right? So x squared plus y squared equals 9, or a circle of radius 3. So our surface integral has turned into a double integral over a nested circular region, a donut, and there's x squared plus y squared floating around in it. And if you're starting to ring some bells here, you're probably thinking polar coordinates. And so we would take this double integral and say, fine. We started with the surface integral. We converted that into a good old-fashioned double integral. In order to evaluate this, it's probably best to use polar coordinates. Isn't this fun? However, now we're in business because polar coordinates is pretty straightforward. So this region goes from r equals 1 to r equals 3, goes all the way around, so theta goes from 0 to 2 pi. This x squared, there's nothing to do with it except call it r cosine theta squared. This x squared plus y squared is r squared. This square root of 2 can come out front. And then the dA part of it, remember in polar coordinates, that becomes r dr d theta. All right, so I've made a big sloppy mess out of this. This is ready to just be typed in and evaluated. So I'm not actually going to do it. We've gotten it to the point where it's a matter of calculation, either by hand or just by having tech do it. The important thing here is the trajectory from the original surface integral to its double integral format that can be calculated using this projection factor from the surface to the xy plane, and then doing that integral however you would have done it a couple of chapters ago when we were talking about double integrals. We will do lots more examples in class after break.